If you've been looking on how to create a computer in Half-Life 2 without scripting and without modding, using just the I/O system of Source Engine, then you've come to the right place. Because I made just that. It's a very simple computer, it doesn't really have much for now. This is where your program is going to be written. These are the different instructions you have. You can copy values from one register to another, add, subtract, multiply, divide them. You have 3 different registers, as well as the program counter P, which is where your program is currently at, on which line, and also F, which is an internal register, which I'll elaborate why we need that later. The registers are all floating point values, which you can either manipulate here using these buttons or later using the instructions. You can also use console commands to, for example, set a register to a decimal number, like 0.5, which you can see is shown using these lines here. The current maximum and minimum values are between -16 and +16. The only reason for that is form factor. These displays here are created by sliding a texture, and the more numbers you want to support, the larger the texture needs to be. But this is easily extensible for the future. There are some RAM experiments over here which have not proven successful yet. So let's create a very simple program, which is going to continuously divide a number by 2. So if you want to have a NOP, like an instruction that does nothing, all you need to do is just leave a line empty. We'll need it here for the first line, which we'll soon see why. We're also going to have a move instruction right here. So our starting configuration will be A set to 10 and B is set to 2. So all math instructions are very similar to Z80 assembly, where the results of any division, or for example, gets always stored into an accumulator register A. So what we're gonna do here is take the value of A divided by B, and the result's always stored in A. So 10 will be divided by 2 to get 5, and then 2.5, and so on. Now to jump, there is no dedicated jump instruction. Instead, you can very simply write to the program counter register, just like with any other register. So by copying the value of C, which is 0, into the program counter, we're basically going to jump back to the first line of code. But since a jump has an off by 1, the first line is not actually going to be read, so it'll basically jump to the line number 1. So the controls available are play and stop for automatic execution, and then we can do step-by-step instruction as well using the blue button. So the NOP does nothing. Now 10 to 0. We're going to step once further, and now we can see 5 is in the accumulator, so 10 divided by 2. You can see the program counter incremented as well, and the temporary register here also got a value. Next we do the jump to 0. Then we do another division, so now we're at 2.5, and so on. Now if we go back and let this play, you can see it slowly goes towards 0. We can also change it in real time, so you can see it always halves until it reaches 0. We can also make it divide by 3, for example, although it's a bit faster to reach 0 in that case. So yeah, that's basically the current capabilities of the computer. It would be very trivial to add more registers. It is a bit more difficult to add more instructions. How all of this works, I'll get to in a moment. But first, we have to talk about I/O, the Source Engine I/O system. Alright, so now we're in Hammer, we're in the map, and before I'll show you how the computer itself works, let's have a closer look at the I/O or input-output system of Source Engine. If you already know all of the intricacies about it, you can simply skip this section. But basically, it's the way that entities in maps can interact with each other. So let's say you have this button here, and you have this door, and you want the button to open the door. Now, in the Gold Source engine, Half-Life 1's engine, you basically only had a name on each entity, and you had a target on each entity. So, for example, the button is targeting the door by telling it its name. Now, Source Engine got a bit more involved with the system, but it still is largely the same principle. In this case, the door has a name door, and the button is called button. And if you want the button to trigger the door, you simply add an output to the button, saying, if I press the button, what should I do? And in this case, the button should go to the door and say, open. And that's it. Now, the event, basically what the condition is that the code is run, is called an output. It has a target entity. It has an input, which is the action, and it has an optional parameter. And those are basically the entire building block of this computer. Because there are some interesting details on this specific system. If multiple entities exist that have the same name, so if we duplicated this door, then you'll see the door text here is bold. This means there's multiple of the same entity name. This is fine though, Source Engine allows that. It's just going to trigger all of the entities with this specific name. You can also add a wildcard. This system is very limited. It basically checks if you have an asterisk. This asterisk can, basically the text check stops after the asterisk. So it can be called door 1, door 2, or door funny something, blah, blah, blah. It doesn't matter. Anything after these the doe in this case, could be replaced with anything due to this wildcard asterisk. And this allows you to, later you'll see that this will allow you to target multiple entities, but also as individual entities at once, which is very powerful. There are also some special targets, such as !self or !activator, which are not necessarily entity names, but rather a specific, like it's an expression that resolves into an entity. So for example, self is just the entity itself. This is great if you have multiple things with the same name and you still want only a specific one to be targeted. Or activator, which is basically what caused the button press in this case to happen. Finally, the most interesting part is the parameter system, because you might be wondering, how do you transfer numbers from one place to another if all you can do is stuff like open, door, or something like that? Well, if we go back to the door and button example here, these aren't just basic door and button entities, but rather they are a button that you can rotate and by holding down the E button, and a move linear entity, which is similar to a door, but it has more control over the position. Now, if an output, or let's start it the other way around, if an input supports a parameter, such as the set position input, then you can specify a number here, for example 0.5, to say the door should be halfway opened. Interestingly enough, move linear also allows numbers beyond this range, so you can, for example, say 5, and it's going to open 5 times as much as it usually would. If you want to carry numbers through, there's also outputs that support parameters, such as, on the button as well, the position output. This output gets fired whenever the button changes its rotation state. So basically, while you're holding down E, this output will continuously fire. And the cool part is, if you leave the parameter override blank, so it says none here, then the value from this output will actually be used as the parameter value. So that means the rotation of the button will directly influence the position of the door. So that means as the button is turning, the door opens. And if the button turns the other way, the door is going to close again slowly. And this exact mechanism is what is used for basically the entire computer here. So this is how the entity setup looks like. The stuff over here is general setup for the map. I can make this a bit bigger. For example, ammo and weapons and lighting and all these things. This is not really that interesting. All of these entities over here are interesting. Now, since I can imagine that you haven't maybe used the I/O system that much, if you have already used it, or maybe you haven't at all, in that case I will also go over the different kinds of entities that we discover here. But the basic functioning, or the basic way this functions, is as follows. Counters are the number one entity for the mathematical operations. A counter has different outputs which allow you to retrieve its current value. It's basically a number store. It starts with some number, it has minimum and maximum values, and then you can retrieve the value from it, or you can change it. For example, addition, subtraction, multiplication, division, which are the basic operators that we have on the computer. Now this mechanism I mentioned before, the number display here, is just a texture that scrolls up and down. This is exactly the mechanism I explained with the button, but instead of the door or this screen here being moved by a button, it instead is being moved by the counter changing value. So you see here the out value. Output is another one of those that has a number in it. It gets fired whenever the counter changes value, and it's going to move the display up and down. And then, of course, these buttons here change the values of the registers. Subtract 1, add 1, and set to 0. That is all very trivial. Now, the opcodes and register things that you can put down in the code section down here are also fairly simple. It's just all of them stacked together in one pile. They're all fizzbox entities, which is just, a way to turn brushes into something you can pick up. Each of them has a unique name, and you can also see there's some other entities here, mainly the point template entity that you can use to spawn it, and the filter activator name entity, which allows you to pick out a specific entity for filtering. So in this case, let's say, okay, let's just look how it's actually done. So when the playhead, this is what I call the program counter's physical component, the playhead. When the playhead is told to move, similar to other registers, it moves into one of these positions on top of the lines. And this isn't just a visual thing, this is also how the program is actually read. You can see here how there is a stack, like a very thick stack of trigger entities. There's a lot of trigger entities in each of these spots. And these 3 spots are exactly the 3 things that get read. It's the opcode that gets read, so move, add, subtract, and then the 2 register places. So like the first register and the second register get read. And we have 1 trigger for each thing that can be in this spot. So for example, we have here the trigger for the division, but if we hide this one, there's also the one for multiplication and so on in this spot. So this way, we can figure out what is in each of the 3 spots. You might think this is already enough, but the main question then arises, how do you combine this information? How do you then do a copy instruction from register A to register C? Because there's way too many combinations. Like, you can try calculating the math for this, but for each opcode, for each combination of registers, you would end up with a very large combinatorial explosion, and we don't want to model all of the combinations in the I/O. So what is instead done is sort of a 3-step process. I'm not going to go too deep into detail on it, but the basic architecture of it works like this. You can see it in the single-step relay the best. So the playhead moves to the next instruction, and then the 3 triggers in order call a touch test. And a touch test is basically a way to ask the trigger, what are you, like, are you touching this entity right now or not? And it's going to say yes or no. You do that in order. You see there's delays over here, so this doesn't all happen at once. There's small delays between each because the order of execution of outputs is not well defined. And then finally, in case we're playing, it's going to autoplay on its own. So this is the entire logic that happens on each step. Now, what do each of the triggers do? First, the register 1 is asked for what it's touching, and depending on what it touches, it either it passes on a value to a case entity. Now, a case entity is basically a way to disambiguate one input based on its parameter. So we're giving it the different, this one we're giving it the different registers, PA, BC, or F. And depending on what we gave it, it runs different code, so to speak. So you can see for each of the different registers here, we have the different handlers, as I call them. And a handler is basically just a relay. And since this is kind of important, a relay is basically a way to, well, relay an I/O event. Now, this sounds very useless at first. Like, why would you have a relay which gets one input and then triggers an output based on that? But besides organization, so that you can, reuse code snippets, so to speak, you can also disable individual relays. And this is going to be very useful for us, since we can, for example, disable all handlers for a specific register, and then only enable one specific handler later. And then when we call all handlers using a wildcard, as we do in the cases here, we basically don't need to know which combination of things we're currently dealing with, because by only having a single of the handlers enabled and the others are disabled, we're going to basically narrow down the code path into one branch rather than having to choose it in another way. So let's go through the hypothetical example that we have a let's go for a copy from A to B. So that means the first register is going to be an A. So that means all A registers, all A register handlers are going to be called. Now there's only one of them, and the only handler operation is copy to F. Now, this is where the mythical F register comes into play. The F register is basically going to be our way to avoid the combinatorial explosion I mentioned earlier. So rather than implementing add, subtract, multiply, divide with any two combinations and storing it into a third possible register, we hard code some things. So let's, for example, say we're doing an addition. So we put the first entry, like the first register parameter, in this case we said A, we're going to put that into F. We're going to store it into F. Then we're going to get the second operand, and we're going to put it into A. And then we're going to add A and F together and store the result in A. So rather than having to set up all of the different combinations, we just have this single combination. It's always going to be an addition between A and F. Now, since F is temporary, it doesn't matter what's inside of that, and since the result always gets put into A, we basically can use A and be sure that we're not overriding something by accident. The only disambiguation now is where do we get the value for f from and the value from a from? And that's what these different handlers here do. I wanted to dive into detail, but I noticed that it's a bit more complicated than I had remembered it. The way to actually transfer values is a bit interesting, so I might still explain that, because you might be wondering, why is there even more counters here then? Well, think of it this way. How would you transfer a value from one register to another? We already know that there is an output that gives us the current value of the counter. We also know that there is a set value input, which allows us to replace the value of the counter. Now, again, we would have the same issue. We have a kind of a combinatorial explosion where we have to be able to set any value into any register. But the smart thing about this is that instead of doing that, we only do transfers through the F register. So even for a copy, even for the move operator, what we do is move the first register into F, and then move the value of F into the second register's destination. And this is done using these intermediate counters. There's basically two columns of counters. There's one for the different operands and one for the different copy operations. So let's look at the copy2 stores first. I call them stores. It doesn't really make much sense, but that's how I had that named here. So the copy2A store, whenever it gets a value, it stores its value inside of A. That's all it does. It also disables itself, and it starts out disabled. And this is where wildcards are gonna be very handy, because if we look over here, we can see that, for example, let's do it on register F. Like, let's do the example again of moving a value between two registers. So if we're storing the value of A inside of F, then we can later enable one of these counters, which can then copy our value from F into another register. So we basically, this logic here is very dumb. It just says, okay, just put the value wherever you designated it to be. But there's separate code which decides which of these registers it's going to be, or which of the stores it's going to be, rather. So you can see, for example, when we're doing an addition to F, we're adding some value to F, then the result is going to be stored in A. And then we tell the F register, hey, you should store your value in A. It's a bit difficult to explain, especially since you don't have the whole mental model of how I even came up with all of this mess. But in essence, we're abusing the fact that the I/O system has a combination of wildcards and implicit parameter passing to kind of create a chain of operations that happens whenever a value gets put into the system. So all of this happens pretty much immediately, with the exception of these small delays that I had to add in order to disambiguate things that happen simultaneously, such as first making sure that the addition succeeds and then telling the F register to store the value somewhere. So this gave a very brief insight on how this works. It is largely more complicated than that, but at least it might show you that there is a lot you can do with Hammer's source engine's I/O system, even if it doesn't seem like it has that much to offer. I had plans to extend the computer further, adding more registers and operators, but judging by how long it took me to reach this state, and by how much brain gymnastics you have to do in order to be able to set up these entities correctly, and making sure that all of it is wired up correctly, if I had like a script that generated this I/O for me for each operator, maybe, but having to create all of these links by hand, mainly the handler stuff and the physics handling and all that, it took way too long to reach this. So I'll rather settle with this very simple edition and just leave it as a as thought for the future, I suppose, to extend this further. Well, that's all. Hope you liked it.